All right, everybody, welcome to Earth Science. We're going to start our next lab when it comes to energy transfers. You guys did one type of energy transfer, radiation, which was the 3-section lab with the lamp radiating lights into those different, either black or shiny can, sand or water, whatever it might have been. All right, so that's like the transfer of energy basically through space. I mean, through the room, right? Now we're going to do conduction, which is going to be actual physical contact. Energy is going to travel through this metal bar. So the classic Earth Science lab that we're going to do with this uses styrofoam cups. Here's the basic setup, the basic premise. I'm not going to actually start it yet. I'll pause it and get it going like that. But we're going to take a cup. Don't worry about what it says. Some say hot and cold. We're going to take one cup and fill it with water that is really cold. I want it ice cold, but I don't want any actual ice cubes in there because it takes heat energy to melt ice cubes. So we just want really cold water, no ice cubes. And then we're going to put a styrofoam lid right inside there, with the theory being that if this is nice and sealed, no energy should be getting into this to warm it up. Now, we know it's not perfect. Like if you've bought a coffee at Dunkin' Donuts, you know, it cools down eventually, right? But that's kind of the idea of it, is that this would ideally stay as cold as possible. And then in another cup, I'm going to take boiled water. Try not to burn myself. And same deal. Put a cap in it. And again, ideally, no energy is coming and going out of this. With the premise of the lab being that then I can take 2 thermometers and stick them into these right through here, into the water. And this metal bar then will be the thing that really conducts the energy across, right? I'll do a separate one here, so I don't have to rip this out. It'll basically look like this, only the bar will be inside the water, right? There, kind of like that. So the idea is that the energy will go from the hot cup into the cold cup, conducting through this metal bar. And if you were here to feel it, you could feel this as the lab gets going and you'll feel that it's hot, right? So we'll measure it as it goes. Again, usually in class, we do this every minute for 30 minutes. I'll do the same deal as we did in the other one. We'll make it every 5. Every 5 minutes, we'll take a temperature and we'll see the rate at which the energy is leaving this one and going to this one. And then we'll try it again with a little bit of a twist and see how that all goes. All right, so let's do the front page first this time. Different than last time. I'm going to shrink myself down a little bit, and I'll blow this up a little bit. In fact, I'll blow it up a little bit even more. So as we're getting our 3 forms of energy transfer down, there's 3 forms we got to get down. Radiation, which was the light, conduction, which is this one, and convection is the last one, which I don't really have a good lab for. We'll figure out what we want to do there. I'm going to write conduction in this right in that metal bar. I'd like you to join me in that. And that we go from, if we label this cup with an H, the heat energy itself is going from the hot cup, conducting through this metal bar, and going down into the cold cup. This one over here will be cold, even though it's hiding behind my head here. Okay. Now, the thing that's going to be different between part 1 of this lab and part 2 of this lab, we're going to basically do this twice, is that what happens is that this bar, like I said, you could touch it. You could have that energy conduct into your finger because you're physically touching it. But what really happens is that some energy is just given off into the room through this bar. And if you did well before Thanksgiving break with that other lab, with the radiation one, you would know what this is. I'll just give you a hint, I suppose. It is radiation, but let's be more specific. It's infrared radiation. There's infrared energy coming off of that bar and entering the room. So it's not perfectly efficient. We're going to see how many degrees do we lose out of the hot cup, how many degrees do we gain into the cold cup, and you're going to find out that you lost more than like made it into the cold cup. If we're going to use degrees as a unit of energy, which isn't really what they are, but we can use it as a measure of that, right? So maybe we'll lose, I don't know, typically we lose 15, 20 degrees out of the hot cup, but maybe only 10 make it into the cold cup. In other words, there's a difference. There's an inefficiency in the system because some infrared radiation comes off this bar and goes out into the room. So what the second part will be is like you do at home. If you go down into your basement and look at your hot water pipes, they probably might, maybe not, but they may have. Basically, it looks like a fun noodle, like a pool noodle wrapped over the bar. And the idea is, hey, you've purchased energy, either propane, electricity, however you're using your hot water heater. Your hot water heater is running off of energy that you bought, and it heats up that water, and then it sends it to the different parts of the house. You don't want that energy that you bought to heat that water. You don't want that energy just radiating up into the basement and doing nothing, right? You want it to efficiently get all the way over to the sink on the other side of the house. So if you wrap those pipes, you do a better job of preserving that energy that you've already paid for. So that's what we'll do in the second part is we'll figure out a way to wrap this all up and see if we can make it more efficient going from the hot into the cold. We'll see if it works. Oftentimes it does, sometimes it doesn't. But that's how it goes. To finish off the notes, energy conducts. Sorry, I'm on an awfully small font too. There we go. Energy conducts through the metal bar from the hot cup into the cold cup. I'll have to shrink it down a little bit here. What we want to look at is how much did the hot cup lose versus how much did the cold cup gain. Also, is there a way we can make the energy transfer more efficient? Ideally, yes, there is. We're going to add insulation. INSULATION. And here in earth science, people always scramble insulation with insolation, that incoming solar radiation. This is literally the insulation, the stuff that keeps your heat energy in your house. State your hypothesis on how you think adding insulation might change the experiment. Do that quick in this blank right here. Create a text box, chuck it in there, and then we'll start. I'm going to reset everything, press pause, and we'll start the lab. Just like the last one, because this is video and it's kind of, it is what it is while we're all home on COVID breaks. I'm going to do it every 5 minutes. So expect a reading for 0, 5, 10, 15, 20, 25, and 30. The other boxes you can just leave blank. And yes, this is the same, like I stole the same document. I didn't make a new lab. There's nothing that changes over these 30 minutes, though. This isn't like 15 minutes of something happening and then another 15 minutes of something happening. This is just going to be a straight run of 30 minutes. We'll see how the hot and the cold do. I'll help you set up those experiments. A couple questions. This should all look familiar. Shouldn't be too big of a deal. All right. Let me pause. Wherever my thing went. There it is. I'll be back and we'll get started. All right. Okay, here we go. Water is reboiled, nice and hot. We're going to do this in Celsius too. And then that'll help, I'll help you set up the graph. Cold water. You guys probably want to see this, not just... All right, then I got this all set up already. We'll drop it down in there. I'm going to let the temperatures kind of regulate and balance out for a quick sec. And then we'll take our 0-minute reading, start the timer, and we're off and running. Okay, let's do it. I'm seeing 97 and 2. So in Celsius, 97 degrees. Just like the last one, I'm probably not going to do this for all of them. But we'll do that. Timer is started. And we're just going to let this rep for a half an hour. But I'll do our usual pause in the video here. I'll see you guys again at about the 5-minute point. All right, we're going to be at the 5-minute mark right up here. Again, we skipped 1 through 4. And let's see what we got. We got hot at 91 and cold at 7. 91 for hot, 7 for cold. We'll see you at the 10-minute mark. All right, so we're coming up to our 10-minute reading. In about 10 seconds here. Maybe I started early. All right. Our hot is at 86, and our cold is at 11. Sound good? That's a 10-minute reading. We will be back. All right, 15 minutes. And again, we're just going to keep on going now. 15 minutes, we don't change anything. We just keep on going. So at 15 minutes, we are at 80 degrees in the hot cup and 14 degrees in the cold cup. Okay. Next one will be 20. And again, nothing changes. You'll just go, that should have gone in the 15 there. Now you'll go down to the 20 for the next reading. I'll be back, and we'll talk about the graph as well. Okay, coming up to the 20-minute reading. Looks like the hot one's going to be at 76. Are we going? Okay, we're going. Hot one's at 76, and cold one is at 15. Should aim that down a little bit more. There you go. That was the 20-minute. We'll be back for 2 more. All right, we'll do the 25-minute reading here. Sorry, 25-minute reading here. We've got the hot at 71 and the cold at 17. 71 and 17. And then what I think we'll do while we wait for the last one is talk about this graph. How are we going to do this? The x-axis is going to be just like the other ones. There was 30 minutes of time throughout the experiments, and you have 30 boxes, so that's nice and easy. We should label. Try not to knock everything over. Time in minutes. And easy peasy. The origin is 0 minutes. Each box is worth a minute. And again, go ahead, label every one, label every other one, do whatever you think. Most people, and I think it's reasonable, we're doing every 5, 3, 4, 5. That still uses an increment of 1 minute per box. So that's great. 6, 7, 8, 9, 10, and so on. Do that right to the end. If you do it right, it should nail 30 right out at the very final point. That one right there should be 30. Okay. Easy enough. Same old news. Over here on the side is going to be temp. I'm going to make my font really small here. And again, if you're watching this in a Chromebook, I know you can't really see this, but I'm saying temp in DEG degrees Celsius, like that. That's all it says over there. What is easiest to do here? We basically, in Celsius, we have to go from 0 to 100, right? Because freezing in Celsius is 0. The ice water one was pretty close to 0. Boiling is 100. The hot one was pretty close to 100. So what we'll do is just that. There's 40 boxes. If we got to deal with a range of 100 degrees, that means each one's worth 2.5, which sounds initially confusing, but it's not so terrible if we just say that 0, 2.5, and then this one will be 5. So basically every other box is worth 5 degrees. 7.5. 10. Getting the idea here. 12.5. 15. It's much easier to do this with a mouse than these touchpads. I sympathize with you. Keep that up. Please label all of them. Don't just skip. But if you do it just right, your check on your own work is that by the time you get to the top, you should nail 100 right on the dot. Okay. And then the graphing will just be, I mean, your call. But a lot of people choose red for hot and blue for cold. I think that's pretty reasonable. So at hot, at 0 minutes, it was 97 degrees. You will have written 95 right there. That's 97 and a half. So 97 is just below that. Your hot starts there. And then in 5 minutes, it's here. 10 minutes, it's here. That line will kind of go down like that as this thing cooled. Cold at 0 minutes was 2 degrees. So blue dot, that middle line is 2.5. So maybe just a touch below it. That's about 2. And then at 5, it went up to this. At 10, it went up to this. That line will slowly increase. Okay. What to do? Let's check our clock. Okay. That is not a dot. Let's talk about the side real quick, and that ought to line us up with our last reading just in time. Get my stupid face out of the way. So how much did the hot cup cool down throughout the experiment? Basically, if it started at 97, what did it go down to by the time that I read this last reading in about 40 seconds? It went down by this many degrees. Don't tell me what it went to. Tell me it went from 97 down to this. Let's say it went down from 97 to 87, which isn't the case. That would be a decrease of 10. So 10 would go in that box. Same thing here. How much did the cool one go up? It started at 2. It went up to, say, 12, which, again, is not true. That would mean it went up by 10. You got to do the math on your own. What's the difference between these numbers? In other words, not all of the energy from the hot made it into the cold. There's an inefficiency in some way. This is actually going to be like a critical number when it comes time to do the final analysis, because we want to know how inefficient was it? How much did we lose? Which is what you're going to do right there. So that gets us to 30 minutes. And that gets us to the end of this video here. Once we say hot cup 67, cold cup 18. 67 and 18. I'm going to write those down. Hot, cold, 67, 18. All right. So that does it for absorption and radiation part 1. Thanks for sticking with me. I know these things can be tedious, but you're doing well. Keep it up, guys. We'll catch you. So long.